This is Math 251. We're beginning section 13.4. We've been working with double integrals. In this section, we're going to move to triple integrals, starting with rectangular coordinates. We'll begin just with the mechanics of evaluating a triple integral. I don't think anything here is really going to surprise you. Essentially, whichever variable you're integrating with respect to, you just treat the others as constants. So in my first example, we've got this triple integral. And we're beginning by saying, let's take the integral of sine of y dz. Since I'm integrating with respect to z, sine y is really a constant. So I'll simply get sine y times z for the value of that integral. And that goes from z equals 0 to z equals sine x. The dx and dy are just out here for later. The usual fundamental theorem of calculus. Plugging in the upper limit of integration, I'll end up with sine y sine x. Minus, when I plug in the lower limit of integration, it's going to become 0. So I won't write that. And then we've got dx dy. My next integral is with respect to x. So sine y still is a constant. But the integral of sine x would be a negative cosine x. I'm going to pull the negative out. And the next goes from 0 to pi. So I'd have sine y times cosine pi, subtract sine y times cosine 0. Cosine pi is negative 1, so that's a minus sine y. And cosine of 0 is 1, so that's also a minus sine y. And since this one said do all work by hand, I'll just finish that up. I've got a negative 2y inside, or excuse me, a negative 2 sine y inside the integral, times a negative 1 on the outside would make that a positive 2, times this integral of sine y dy. And integrating sine y is going to give me a negative cosine y from 0 to pi. So I'd have negative 2 cosine pi minus a negative or plus 2 cosine 0. Again, cosine pi is negative 1, while cosine of 0 is 1. So I end up with 2 plus 2, or 4, for the value of that integral. So really, more of the same, only more so, is what we're doing here. Same idea as with the double integrals. All right, I'd like to back off the calculation for just a little bit and talk a little bit more about sort of what's happening here. If you think back to single integrals, what we did before this class, the limits of integration, the a and the b, really represent just an interval, right? If you're integrating dx, it represents an interval on the x-axis. When we were doing double integrals, we had the double integral of some function dA over a region R, and the limits of integration, whatever they are, represent some two-dimensional region R. So in a single integral, our limits of integration represent a one-dimensional interval. In a double integral, the limits of integration represent a two-dimensional region. hopefully it makes sense to you that in a triple integral, the thing that we're integrating over, we're going to call it d typically, is actually going to represent a three-dimensional object. I'm just going to call it an object for now, but the idea here is you'd have some three-dimensional object that is your limits of integration, represented by your limits of integration. All right, let's think about the differentials. There was only one way to write the differential here because there is only one differential, dx. We saw that in the double integral, we could either do dx dy or dy dx. There were two ways, two orders that we could do that in. What about now? How many possible orders of integration would we have? Well, dv is dx, dy, dz. How many different ways can you rearrange those? Well, I could keep the dx first and go with dz, dy. I could put the dy first and either go dx, dz or dz, dx. Or I could make the dz go first and then either dx, dy or dy, dx. So that is a total of 6 different possible orders of integration that we could have for a triple integral. We're going to take a look at that a little bit more closely in the chart on the next page. So, if I'm going to kind of make a little sketch of my solid, we'll then talk about how the integral breaks down for that solid, and then we also need to talk about something about the region R. I'm going to start by imagining that I've got a solid with some function z equals g of x and y below, and then another function z equals h of x and y above. When I go to set up my integral, what happens here is that I'm going to start by saying let's integrate from the lower z value to the upper z value. So whatever my function is, f of x, y, and z, I'm going to start with dz. Lower z value is g of x and y, and the upper z value is h of x and y. I'm kind of imagining that I've got this little three-dimensional column between the lower surface and the upper surface. So I'm going from bottom to top. These two surfaces then are going to intersect in a region which could be projected into the xy plane. So I'm going to call this the region R, and I'm going to say that I have to integrate that dA, where the dA is either dx dy or dy dx. The region R then is in the xy plane. All right, so that would be one possible setup. How else might this look? Well, another possibility might be that I'm going to start by integrating from left to right. So maybe I've got a surface over here that's defined as y equals some function g of x and z. And then I've got another surface over here, y equals some function h of x and z. in that case, I want to think first about going from left to right. Again, think of it like a little column in between there. So I'm going to take my original integrand, f of x, y, and z, and I'm going to integrate dy first this time. Going from left to right, that would be from g of x and z to h of x and z. From left to right. The other two variables, the x and the z, are going to be my dA over some region R, where the dA this time is either dx dz or dz dx. So R is in the xz plane. If I were to draw it, my R would look like this, the intersection between my two surfaces again. All right, one last picture. What if I have a front-to-back situation? I'm not wild about that drawing. I'll tell you what, I'm going to try that one more time. Squeeze it in up here. So I'm going from the back to the front. It's the hardest one for me to draw. The back here would be x equals g of y and z, and the front would be x equals h of y and z. Now when I go to set up my integral, again, I've got whatever my integrand is, f of x, y, and z, and I'm integrating dx first. From the back, g of y and z, to the front, h of y and z. The region R this time, this intersection, is going to define the dA part. And since I've already done dx, this will either be dy dz or dz dy. In other words, R is in the yz plane. All right, if that all seems a little bit abstract to you right now, don't worry, we're going to do an example all three ways, so you'll be able to get a little bit better feel for it in the next video.